Hello everyone, it's Mr. Woodward. In this video, we're going to talk about what happens when you've got a projectile that's being launched at an angle. How can you use trigonometry to figure out that angle and figure out the components of the velocity? Let's take a look here. So far we've looked at projectiles that have been launched horizontally, such as a ball rolling off a table, a car driving off a cliff, or a gun shooting a bullet at a level target. However, most projectiles aren't launched horizontally, but are instead launched at angles above or below the horizon. In the picture below, notice the variety of angles that a soccer ball can be kicked towards a goal with various levels of success. So we have these angles that are being measured with respect to the horizontal. So this is 15 degrees, right, with respect to this horizontal. This is 75 degrees, should be this angle with respect to this horizontal, okay? This is theta. Moving on, since we have kinematic equations for the horizontal and vertical directions of motion, it's often necessary to break up the initial velocity of a projectile into its horizontal and vertical components. Okay, you can do this by drawing a right triangle where the initial velocity is the hypotenuse, the horizontal velocity is the adjacent side, and the vertical velocity is the opposite side of that triangle. And this is only when you are measuring the angle from the horizontal. So let's take a look at an example. So let's say you've got this initial velocity vector here, right? And this is similar to the vectors that were drawn up here, right? You've got these various angles where a soccer ball is being kicked. So let's say we're looking at the 30-degree example here, okay? So you've got this angle, and you want to break it up into its components, okay? So this right here represents the initial the initial velocity at an angle, and we want to break it up into its components so that we've got the initial velocity, and part of it is going to be broken up into its vertical component, VIY. The other part of it is going to be broken up into its horizontal component, VIX. Okay, and here's that angle still, 30 degrees. So doing a little bit of trigonometry, we're going to essentially take this vector here and we're going to like move it over to here, to this side of the triangle, okay? And we're going to redraw. So what would that look like? So you'd have now the original vector here, and then you'd have the horizontal component coming out this way and the vertical component coming this way, okay? So this is VI, this is VIX, this is VIY, and then this is that 30-degree angle. Okay, once we have it recreated into a triangle, we can use some of the trigonometric functions, sine, cosine, and tangent, to actually figure out the values of these different components. We'll take a look at that in a second. Okay. What if, however, the angle is measured from the vertical, right? So same triangle as before. Last time we measured, 30 degrees from here, but you can also do the same thing, but measure the angle from the vertical. So in this case, we'd have 60 degrees from the vertical for the same vector. So this is still the initial velocity. And when we break it up into a triangle, we now have the initial vector here. The vertical component would still be that part. The horizontal component would be this part. But now we're measuring from here, 60 degrees. So now instead I'm going to imagine that I could take this vector, right, and move it. And I need to try that more carefully. Imagine I could take this vector here and move it up to here and recreate like a new triangle, right? So what would that look like? So I'm going to have my original vector which is the, real life initial velocity, but then broken up into its vertical component and its horizontal component this way. So this is VIX, this is VIY, and this is that 60-degree angle. Once you've represented the initial velocity as a triangle, which is what we did here, with horizontal and vertical sides, you can calculate the lengths of the sides using sine, cosine, and tangent, right? So if the angle is measured from the horizontal, then these would be labeled as such. Your opposite side, this would be your opposite side, this would be your adjacent side, and this is the hypotenuse here, okay? And then sine, cosine, and tangent relate them to each other, right? Sine is the opposite. The sine of this angle would be the length of this leg divided by the hypotenuse. That's what we're talking about here. The cosine of the angle would be the length of the adjacent leg, this side, divided by the length of this side, the hypotenuse. And the tangent of the angle would be the, here tangent, would be the length of the opposite side divided by the length of the adjacent side here. Now, you can do the same thing, sine, cosine, and tangent, if you've measured the angle from the vertical. It's just that you would draw your triangle a little bit differently. So you'd have the same triangle, but now you would just measure it this way, the angle measured from the vertical. This is your hypotenuse, as before, but now this leg would be your adjacent, and this would be your opposite side, right? It's all with respect to the angle. Let's take a look at a couple of examples here together. So suppose we've got this volcano. It's spewing out some molten rock at an angle of 35 degrees with an initial velocity of 25 meters per second. How would we break up that velocity into its vertical and its horizontal components? Well, first of all, we would relate them in a triangle. So here's that 25 meter per second vector. And maybe I should draw it in green like it is in the picture. Here's the 25 meter per second vector. The horizontal component would be here. The vertical component would be this side, the opposite. And the 25 meters per second, we would just call, this is just VI, right? It's not vertical or horizontal. It's the it's called the resultant velocity. So if we want to solve for the horizontal velocity, if we want to figure out what this one is, right here, then we would want to identify that Vx is the adjacent side, right? So what relates the adjacent side to the hypotenuse, which is here? Cosine does. So we would say the cosine of 35 degrees is equal to the adjacent leg, which we're calling Vx, divided by the hypotenuse, which is the 25 meters per second side. Okay? Multiplying both sides by 25, I get that Vx equals 25 meters per second times the cosine of 35 degrees. So I would get that the value of Vx is 20.5 meters per second. And so I could put that here, 20.5 meters per second. Okay, what's the vertical component of that velocity? Well, if I want to solve for Vy now, if now I'm looking at this, it is, so compared to this 35 degrees, right, this is now the opposite leg And I'm going to compare that to what I know here, which is the hypotenuse. So what relates opposite and hypotenuse? That's sine. So, so Vy is now the opposite leg. And so I can use sine of 35 degrees is by definition the opposite leg, which is Vy, divided by the hypotenuse, 25 meters per second. Multiplying both sides by 25, I get that Vy is going to be 25 meters per second times the sine, 35 degrees. And so the value of the vertical component of the velocity is 14.3 meters per second. And I could add that over here. Okay, so now I have successfully broken up this initial velocity into its vertical and its horizontal components, okay? Where the vertical component is 14.3 meters per second, the horizontal component of that velocity is 20.5 meters per second. Once I have those components, then I can use those in the big three kinematic equations to solve all sorts of other stuff. For example, I would use this vertical component to figure out how high the projectile goes, and I could use the horizontal component here to figure out how far it goes, what the range of that trajectory is.